on to section 3.6 where we're going to expand upon what we have done in section 3.5 a little bit, but using a different type of number. So before we do that, we need to learn about complex numbers. So when finding the zeros of a polynomial, at some point you'll be faced with a problem like x squared equals -1. Well, there are clearly no real numbers that are solutions to that, because if I ask what number do you square in order to get a -1, the common answer I get is -1, but -1 times -1 is a positive 1. So there is never a number that you can square to get a negative number. So therefore, things kind of are left with a certain feeling of incompleteness. So to address this, we need to talk about an imaginary unit, and mathematicians call that unit I. So the imaginary number I, which is usually done with a script I, most basic number is I, and it is defined to be the square root of -1. So that is something very important that you need to make sure that you remember. Now, that's commonly called the imaginary number, and for any real number or real multiple of I, it is also considered an imaginary number. So for problems to come, we will also need what I squared is equivalent to. So I'm going to take this I equaling the square root of -1, and I'm going to square both sides. Because on the left side, that becomes an I squared. On the right side, that square and square root cancel each other out, leaving me that I squared is going to be defined to be -1. Now, when we operate here in just a little bit with our complex numbers, we're going to have to remember that fact. So, I then am going to look at this first problem where we asked to simplify. And on simplifications, you have to basically not leave a square root underneath that radical, nor do we want to leave a perfect square under that radical either. Now, if I said that you asked you for the square root of 4, hopefully you would tell me 2. But now I have this -4 under there, okay? 2 times 2 here gives me 4. The square root of 9 is 3, because 3 times 3 gives me 9. But again, there's no number that I multiply by itself to give me a -4. So this is where using the square root of -1 is important. So I'm going to break this as 2 factors. For -4, hopefully you agree that -1 times 4 is -4. Now that I've split that up, this square root of -1 I can replace with an I, and the square root of 4 is still going to be 2 in real numbers. But notice that I don't write this as I2, just like we wouldn't write 2x as x2. I'm going to write this as 2I, and that's going to be my final answer. Now, I can, again, do 36 times a -1. This time I reverse the order to make it a little bit easier. This gives me a 6. Square root of -1 is an I, therefore 6I would be my answer there. So in layman's terms, basically, that's the math behind it. But if you ever have a negative underneath the square root, you basically bring it out to the front and make it an I. And then do the square root that's underneath there. Okay, so using that idea, if I have a negative, I'm going to bring it out and make it an I. And what's the square root of 81? Well, it will be 9I. Minus the square root of -25. The square root of 25 is 5. Bring that out. Gives me an I. Now, again, we don't want to leave this incomplete. 9I minus 5I would be just like if you're combining like terms of like 9 apples minus 5 apples gives you 4 apples. So 9I minus 5I is 4I. Moving on to our last simplified version here, we have to simplify this and this first. So I'm going to rewrite the -3. Square root of 100 is 10. With the negative, that comes out front and brings an I. Minus, well, that's just the square root of -1, which is the definition, so I'm going to subtract I. -3 times a 10I. Just like if I said -3 times 10x, you would tell me -30x. But here, we're going to use it as an imaginary, so -30I minus I, just like before, combining like terms, gives me a -31I, and that would be my final answer. So that is what we refer to, or those are what we refer to as imaginary numbers. Now, Imaginary numbers are something that we can kind of put together. What we have worked with in the whole course already are real numbers, which with real numbers, we have rational numbers and irrational numbers. Part of rational numbers means then that I have integers. Then, with integers, I end up having whole numbers. And then in the end, the very most restricted set is natural numbers. So, real numbers, and then we also have these imaginary numbers. Well, where we are going now is that I'm going to put those two together and deal with complex numbers. Okay? So that's kind of the big kahuna number set, is the complex numbers that are broken into imaginaries, broken into reals, and we can now be able to investigate that a little bit more and operate that with some numbers. Oops, I went too far. All right, so a complex number is a number, z, equaling a plus bi, where a and b are going to be real numbers. A is what we refer to as the real part, and b is referred to as the imaginary part because the b is attached to the I, so that should make sense. And notice that the imaginary part is always written second, so don't put the I in front, always put it at the end. So if these are a number system, then we should be able to operate with these numbers, and that's exactly what we're going to do next. We are going to do, first off, some addition, then some subtraction, then some multiplying and dividing. So if you recall, when you have a plus between two numbers, then with that parenthesis, things aren't going to change. With these two complex numbers, you can kind of think about a plus 1 that's multiplied through, doesn't change anything, gives me a negative 2 plus a 7i. And like I said, this is very similar to combining like terms. I'm going to combine the real pieces together, then I'm going to combine the imaginary pieces together. So 3 minus 2 gives me a 1. Negative 4i plus 7i is a positive 3i. And that's my ending complex result. Moving to a subtraction, I now need to distribute that negative. It does make a difference when you have a minus there. The first one stays the same, but the negative times a negative is a positive 2, and a negative times a positive is a minus 7i. So you must distribute that negative first, then combine your terms. So I'm going to combine my real terms. 3 plus 2 gives me a 5. Negative 4i minus 7i is a negative 11i. And that's going to be my answer. That is a complex number. It has a real part of 5 and an imaginary part of negative 11i. All right, moving right along. We end up having multiplying a complex number by a real number. 5 is a real number times this complex number. We're going to treat it as distributing. We're going to multiply 5 times 2 to get 10, and 5 times a negative 3i to give us a negative 15i. As part of my complex number, and that would be my answer. But be careful that you have an imaginary number times a complex number, because now we're going to have multiple i's in there. So 4i times a negative 5 would give me a negative 20i, but a 4i times a negative 3i, notice the two i's there, I get a minus 12i squared. Now this reverts back to the opposite side of this paper when we talked about what I squared was equal to. As a reminder, I squared is equal to negative 1. So if you get an expression in terms of I squared, it's not a complex number with I squared in it. So you have to get rid of that I squared, exchange that for a negative 1. So I'm going to replace basically I squared with a negative 1. And what happens? Well, 1 times 12 is still 12, but a negative times a negative ends up becoming a positive. So in layman's terms, basically with this I squared here, it's going to switch the sign of that. Now, that is the real piece, so I'm just going to start with that piece and write it in front, then attach my imaginary piece, negative 20i, in the end. So that would be my final answer there for that imaginary times a complex number. All right, so the next four are going to be dealing with some foiling. So I hope that you recognize and see these two binomials as foils. So it's very similar to doing some expressions of operating those. So for first, outer, inner, last, we're going to multiply here 3 times negative 2 to get negative 6. Outside gives me a plus 21i. Inside is a negative, a negative times a negative is a positive, so a positive 8i. And my last term ends up with a negative 28i squared. There's that I squared hanging out again. We cannot leave our terms in I squared. Remember, it is a negative 1. So here's what I do normally for a shortcut. Once I get an I squared, I'm going to mark it out, and I'm going to change the sign. Let me actually do that with color, a different color change. Mark this out, change the sign. Now I can combine my real pieces, 28 minus 6, or negative 6 plus 28 is 22. And I can combine my imaginary pieces to get a plus 29i, and that would be my final answer. So foil, foil, foil. Now, here comes this next problem that I intentionally put one like this on here. Because please do not just bring in that square. You can't do that because of that minus right there. Remember, you have got to write this out twice and foil it if you would encounter a problem with that square. So I'm going to take that out and do 3 minus 4i. And now we get to foil, okay? So I'm going to go 3 times 3, which is 9. Outside gives me a negative 12i. Inside also gives me a negative 12i, and that's what you should get when you're squaring something. These inner pieces should be the same. And then the outside there, negative times negative is a positive. 4 and 4 is 16. I and I is I squared. But here we go with I squared. I squared is negative 1, therefore I'm going to change the sign on that. I'm going to combine my real parts. 9 minus 16 is negative 7. And combine my imaginary parts, which is a minus 24i. And that would be my final complex number. Okay? All right. Next one. Still two binomials that I'm multiplying together, but I hope you recognize this as one of those special cases where we are looking at doing a difference of squares. So with the difference of squares, we'll see what happens every single time, okay? So let's just FOIL. 3 times 3 is 9. Outside would be a plus 12i. Inside is a minus 12i. And my last terms become a negative 16i squared. If you're so inclined to change that I squared to the first, go ahead and do so, making that a plus 16. But in a difference of square situation, your outside and inside terms should always cancel. This should cancel that. And that is kind of part of that difference of squares that we saw when we were factoring. But in the end, basically all I'm left with are these real pieces, which the answer would be 25. And you say, well, that doesn't look like a complex number. Well, in disguise, it actually is. It is 25 for the real piece and 0 on the imaginary piece. Now, we don't go around writing our numbers like this whatsoever, so I don't expect you to write that. But if it does cancel out on the imaginaries, remember, this is still a complex number, okay, even though it is just a real piece. So 25 would be our answer. Now, we're going to actually be seeing this kind of idea on the back side of this paper when we are dividing two complex numbers, okay? All right, this next example, basically, we are looking at being able to simplify, but before we can simplify by multiplying and FOILing, we have to take care of these square roots first. So never can you operate with that negative underneath that radical. Simplify it to what we know it is. So 3 minus, remember, the square root of 9 is 3. Bring the negative out front, becomes an I. So net 3 minus 3i times a 1 minus 2i would be what I get whenever I simplify that. So now we have to FOIL. So we go 3 times 1 is 3. Outside gives me a minus 6i. Inside is a minus 3i. And my last term here, negative times negative is a positive, 6i squared. Immediately cross that out, make that its opposite, and we're ready to go. So 3 minus 6 is a minus 3. Negative 6i minus 3i is a negative 9i, and that is my final answer. Okay, that is a complex number. All right, very, very good. So now we're going to end up kind of doing some division of imaginary numbers and division of complex numbers. First up, the imaginary numbers. When dividing complex numbers, we have to devise a way to write the answer as a complex number. Looking at what I have in this example, that is not a complex number because I have an I in the bottom. So in order to do this, with just an imaginary number in the denominator, we are going to multiply top and bottom by I. That's the strategy to get that out of the bottom. So I'm going to multiply the bottom by I, and I'm going to multiply the top by I. So when I do that, this I has to be distributed to each one of these. So I'm going to write that as minus 4i plus 2i squared. Oh, there's an I squared. Can't have that. I'm going to make that a minus. All over, this gives me a 3i squared. And again, I can't have I squared, so I'm going to mark it out and make it its opposite. So what I get down to is this. Now notice in the top I have my real piece, then my imaginary. I'm going to flip-flop that because my imaginary should come second. So this is what I have. Now, this is not a complex number because I have like an overall fraction here. To make it a complex number, we have got to take the real pieces and divide by negative 3. So negative 2 divided by negative 3 can be simplified to be just a 2/3 by changing those signs. But I also want to distribute that negative 3 to the imaginary piece. So that gives me a negative divided by a negative, which is a positive. And the best that I can write that 4 over 3 is 4/3 and attach the I at the end. Therefore, that is the imaginary, the complex number with the real part and the imaginary part of that complex number. Okay? Now, in order to divide two complex numbers, though, we need an extra piece added in. And that extra piece, when we are dividing a complex number in the denominator, one has to know the meaning of a conjugate. Okay? The conjugates of a complex number, a plus bi, is the number a minus bi. So what did I do? The a's are still the same, but the b's are now the opposite. So therefore, the sign of the imaginary piece, or the imaginary part, is changed to its opposite sign. So I have a couple examples here for us just to practice. If I have the complex number 3 minus 2i, the only thing that's going to change is the sign of the imaginary number. That becomes 3 plus 2i. If I have negative 5 minus I, negative 5 plus I is the conjugate. This is an imaginary piece, therefore I should be able to change to its opposite. Now, if you recall, 0 plus 5i is going to be the same as 5i. That's going to be the complex version with the real piece and the imaginary piece. So if I think of it that way, 0 minus 5i is going to be the conjugate, or get rid of the 0, and technically negative 5i would be it. Then we move into 4 plus 6i. So take the opposite of the imaginary part, 4 minus 6i, and negative 7 minus 9i would be the conjugate of this one. Okay? Now, why do we need to know that? Well, we need to know that because when I'm dividing these two complex fractions, like what I have in this example, we are going to multiply the top and the bottom of the fraction by the conjugate of the denominator. So the problem is that I have those i's in the bottom. I can't create a complex number without getting that out of there. Okay? So in the denominator, I have 4 minus I. What is the conjugate of 4 minus I? Well, in that case, I'm going to change the imaginary part and make that 4 plus I. So I'm going to multiply top and bottom by 4 plus I. Now, from here, basically, it's two foiling problems in one. I have a foiling problem on the top and a foiling problem on the bottom. So if I do that on the top, we're going to go 2 times 4, which is 8. Outside is a plus 2i. You may be able to do it without the arcs. Plus 20i on the inside. And the last term looks like a plus 5i squared. Get used to that I squared crossing out. Makes that a minus. On the bottom, the first term is a 16. The outside term is a plus 4i. The inside term is a minus 4i. And the last term here gives you a minus I squared. Negative I times I is I squared. Again, I squared is negative 1. I'm going to make that a plus, but I don't really see my 1 here. So you might want to just put that on there, like that. Okay, now, why do we have to do the denominator, the conjugate of in the denominator? Well, if you notice, this 4 minus I and 4 plus I is very similar to that difference of squares one that I talked about on the reverse side where we just got the answer of a 25. So what's going to always happen is that your denominator should have things that cancel. That outside and inside should always cancel if you're multiplying by the right conjugate. So I'm going to combine on the top the 8 minus the 5 to give me a 3 and the 2i plus the 20i to give me a 22i. All over, once these cancel, I'm left with 16 and 1 to give me a 17. Now, to technically get it into a real part and an imaginary part, we have to undo kind of that denominator and be able to distribute that to both. So, by the idea of undoing a whole fraction, I can distribute the 17 to the 3 and the 17 to the 22. If anything were to be able to cancel, you definitely can. So 3/17 plus 22/17i is the complex number. Okay? Alright, let's try this next one. This next one is dividing two complex numbers. Again, we're going to multiply by the conjugate of the denominator, which if I have 2 plus 3i, then it's 2 minus 3i is my conjugate. And that's what I must multiply the top by as well. So we're going to then, at that point, make it a FOIL problem. Negative 1 times 2 is minus 2. Outside is a plus 3i. Inside is a plus 6i. And my last term here is a minus 9i squared. We're going to cancel out the I squared and make that a plus. Then, on the bottom, 2 times 2 is 4. Outside is minus 6i. This is where it should cancel. This gives me a plus 6i, which is good. And the last one is, again, a negative 9i squared, making that a positive 9 in the end. Simplifying the top, a negative 2 plus 9 is a 7. Plus 3i plus 6i is a 9i. All over, these are gone, leaving me with 4 plus 9, which is 13. So again, technicalities, making sure that this is a real part of 7/13 plus 9/13 I, and that would be your final answer. Okay. All right, very good. Now, we're going to solve 3 equations. The first 2 have a power of 2. There are 2 ways that we've learned how to solve quadratic. I said 3 ways. One by factoring, one by completing the square, and one by the quadratic formula. We are going to hone back in on that quadratic formula, which we just saw in section 3.5. As a reminder, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We're going to use that. So, if I encounter this polynomial, I'm first going to see, can I multiply to get 5, that I add those numbers to get 2? And the answer to that is no. So unfortunately, we can't factor, which is the easiest. The next easiest would be to do the quadratic formula. Okay, so I'm going to let this be a, this is b, and that is c. So let's do it. X equals negative b, so the opposite of negative 2 is 2. Plus or minus the square root of b squared minus 4 times a times c. So I got this 4 by squaring that 2. All over 2a, which is 1. All right. Simplifying underneath that radical, I get 2 plus or minus. Now we have 4. This gives me 20, so what's 4 minus 20? Well, that's negative 16 all over 2. I'm hoping that you recognize that negative 16 as, well, if it was 16, I could take the square root and it would be 4. But since it's a negative 16, I can't do that just by leaving 4. I have to bring that negative out front and make it an I. So I get 2 plus or minus, now square root of 16 is 4, I for the negative, all over 2. Now, number 1, this isn't a complex number, but the other thing is I have some common terms here. This can be, if I simplify this down, 2 over 2 gives me a 1. And if I simplify this down, I get 1 plus or minus a 2i as my final answer. So when you're simplifying, make sure you can divide all of them and make simplify or reduce. If not, don't reduce any of them. Okay? Now, if they ask you to write your answers in separate form, this would be the same as 1 plus 2i and 1 minus 2i if I break apart that plus or minus. So not too bad with that. Okay? Now, the next quadratic is good, except for it's not equal to 0. So the first thing I want to do is to add that 19 over to both sides. So I get 2x squared plus x plus 9 equals 0. Now, again, you can try to factor this polynomial, but no matter how you try to factor it, it will not factor. So we're going to resort back to the quadratic formula. Okay, so I'm going to let A be 2, B is 1, C is 9. So we get x equals negative B plus or minus the square root of B squared, so squaring 1, minus 4 times A times C all over 2A. So I'm going to simplify underneath there, and I again need to multiply here. 4 times 2 is 8 times 9 is 72. 1 minus the 72 is the negative 71 all over 4. Now again, that negative, you should be kind of, the little flag should be waving a little bit. That negative has to come out front and make that a positive, or excuse me, not a positive, makes it an I, an imaginary, all over that 4, and that would be your final answer. Again, they may ask you to do one of two things. They may ask you to separate them into real pieces and imaginary pieces, so you would have something like this for the complex, and then the negative version of that minus the square root of 71 over 4i. So this may be the way that they want you to write that or type that in My Open Math. Okay? All right, very good. Last problem. It's going to kind of mold what we did in section 3.5 to our complex numbers. So if I'm trying to solve a cubic equation when it's equal to 0, we are going to bring in Cauchy's bound, which was the m and a sub n. So going back to section 3.5, remember m was the largest number in my polynomial's coefficients, which is 8. A sub n is the leading coefficient, which is 1. So I would end up doing the opposite of m over the absolute value of a sub n minus 1, and the 8 over a sub n and absolute value plus 1. So if you were to simplify both of these, this becomes right here a negative 8 minus 1, so negative 9, and 8 divided by that 1 plus 1 gives me a positive 9. So there's the bound that it is in. But what if we also want to kind of break down that possibilities with our rational root theorem? Well, the rational root theorem says that I need factors for p and factors for q. Then we're going to look at our p over q's, okay, as the possibilities with plus or minus. P comes from the constant term. So the factors of 8 are 1 and 8, 2 and 4. And the q comes from the leading coefficient. Therefore, the only factor of 1 is 1. So when I do all combinations of 1 over 1, 2 over 1, technically we just get the plus or minus version of all of those numbers as factors of p. So, again, when we have this, the next step to solve is to take one of these possibilities along with our synthetic division of each of these coefficients, so 1, minus 2, 5, and 8. Let's see if we get a remainder of 0, and then we can factor the rest. So we get a 1, multiply by the 1 out front gives me a 1, add gives me negative 1, multiply is negative 1, add gives me a 4, multiply by 1 gives me a 4, and unfortunately, I don't have a 0 as my answer, so therefore, as my remainder, therefore 1 is not a root. So let's go to the next possibility of negative 1. Again, rewrite the coefficients of your polynomial. Bring the 1 straight down and multiply by negative 1 to give me negative 1. Add gives me negative 3. Multiply is a positive 3. Add vertically gives me an 8. Multiply by negative 1 is a negative 8. And oh, that looks good. There's my 0. So therefore, negative 1 is a root or a 0. I now need to go out and find the other 2. Well, if you recall, this is an x cubed. Therefore, this, when I divide, has to be an x squared. So extract out this polynomial. I get x squared minus 3x plus 8. And if I try to factor that, what do you multiply to get 8 that you add to get 3? Well, there's nothing. 1 and 8 adds to get 9. 2 and 4 adds to get 6, not 3. Therefore, we must use the quadratic formula here in order to solve. So one more time on the quadratic, we're going to go x equals negative b, so 3 plus or minus the square root of b squared minus 4 times a times c, which is 8, all over 2a, which is 1. Simplifying gives me 3 plus or minus the square root. Well, 4 times 1 times 8 is 32. 9 minus 32 is negative 23, all over 2. And I can end that by saying I have to bring that negative out. So that becomes an imaginary out front of that square root of 23, all over 2. And now that is my final answer. So, again, you can split it up if you want, but the 3 answers that work, don't forget, negative 1 was the first one that we found. 3 plus I root 23 over 2 is the second, and 3 minus I root 23 all over 2 is the third. And that is the final solution for that quadratic equation. Okay? So, make sure that you are able to build upon this. So the Cauchy's bound and the P's over Q's was from the previous section. Being able to find the 0, that was from section 3-4. So everything builds, and we're just going to kind of keep building a little bit here through chapter 3 until we get to chapter 4 where it'll be a little bit of a different concept. So until next time.